This is Professor Mark Barkey. In the last lecture, we talked about how the maximum dissipation postulate led to the normality flow rule. This lecture, we're going to get into the details of the normality flow rule. We're going to see how we can write it in terms of deviatoric stresses for a given yield criterion. And we're going to calibrate it to a uniaxial stress strain curve. We're building up to our complete J2 plasticity theory. All right, so let's call this E. And in the previous lecture, we talked about how the plastic strain increments were proportional to the partial derivative of the yield function with respect to the stresses. And we're going to say that that is proportional to some unit normal vector to the yield surface. We can use I and J, or we can just say Ni. If we're thinking of our 9-dimensional space, where we have some surface here and this direction. This is partial of f with respect to sigma ij. This is a function of sigma ij, and the unit normal would be in that same direction. Of course, it would be a unit direction. It would be like that. So we're going to get into the details and see how we can write this. But what I wanted to do at this point was show that if we cast our yield function in terms of deviatoric stresses, the partial of f with respect to the deviatoric stresses is also in the same direction as partial of f with respect to sigma ij. Just as a reminder, deviatoric stresses can be expressed in terms of regular stresses as sigma ij minus 1/3 Kronecker delta ij sigma kk, where we're using our index notation. And the deviatoric stresses effectively remove the effect of hydrostatic stress from the stress tensor. And due to our assumption that a lot of our metals are yield independent of hydrostatic stress. Now, of course, if you have a yield function or a material that is depending on hydrostatic stress, then you'd have to be careful about applying what we're going to show next. And you'd have to stick to regular stress space in the normality flow rule if you wanted to do that. Alright, so let's just say here we will see that the partial of the yield function in terms of sigma ij, or this is a function of sigma ij, is the same, or it leads to the same unit normal. Let's put it that way. It's proportional to the partial derivative of the yield function in terms of deviatoric stresses with respect to Sij. And there's no sum on these terms. I need to make this a little bit more clear. Let's put a squiggle underneath here instead of the I and J. Alright. So let's start with a clean page, and we'll get to work. Alright, so if we want the partial derivative of our yield function f with respect to sigma ij, what we can do is we can use our calculus to write this as partial of f with respect to s, say mn, and the partial derivative of smn with respect to sigma ij. So now smn is equal to sigma mn minus 1/3 Kronecker delta mn sigma kk. So let's evaluate this first. We're going to take the partial derivative of smn with respect to sigma ij. So the partial derivative of sigma mn with respect to sigma ij. And then we have minus 1/3 Kronecker delta, and we have mn, and then we have partial derivative of sigma kk. Now, remember, that's the trace of the stress tensor. It's the summation notation that we're using, so it's sigma 1,1 plus 2,2 plus 3,3 with respect to sigma ij. Now this first term right here is kind of interesting. We'll only get 1 if I and M are equal and if J and N are equal. Well, the way we can express that in our index notation is Kronecker delta I M, Kronecker delta J N. Then we have that next term, minus 1/3 Kronecker delta Mn. And this next term right here is the partial derivative of sigma 1,1 plus sigma 2,2 plus sigma 3,3 with respect to sigma ij. Well, we'll only get 1 if I and j are both equal to each other. Okay, as we evaluate that partial derivative. And so we can express this as Kronecker delta ij. So now here we have the first term in this chain rule of differentiation that we have here. Alright, so let's go ahead and write the expression. Partial of f with respect to sigma ij is partial of f with respect to Smn times this expression, Kronecker delta Im, Kronecker delta Jn minus 1/3 Kronecker delta Mn, Kronecker delta Ij. And at this point we can expand these terms out. Alright, so first we'll just do an algebraic expansion. Partial of f with respect to Smn, Kronecker delta Im, Kronecker delta Jn minus 1/3. Partial of f with respect to Smn, Kronecker delta Mn, Kronecker delta Ij. It's a j right here. Using our Kronecker deltas, acting as a replacement operator, we can replace the m with an I and the n with a j. So here we have on our first term partial derivative of f with respect to Sij. And on this next term, here we have 1/3. We have Kronecker delta Ij. And then we have the partial derivative of f with respect to the partial derivative of Smm. Now Smm is equal to the trace of the deviatoric stress tensor. And we want to think of it in terms of function. We don't want to divide by 0, but if we think of that in terms of the function, we have assumed that our function f is a function only of J2 and J3 for hydrostatic stress independent yield criteria. So then with f not being a function of J1, this term goes to 0. And then we finally arrive at the result that we want. Partial derivative of f with respect to sigma ij will end up being the same as the partial derivative of f with respect to Sij. In other words, under these conditions, the unit normals of the yield surface expressed either in terms of deviatoric stresses or in terms of regular stresses are going to be the same. Now at this point we're going to take a further simplification, but it's a good one. For J2 plasticity theory, we're going to take our yield function f to be defined as Sij Sij and equal to 2/3 sigma naught squared. J2 is equal to 1/2 Sij Sij. So if we want, we can set that equal to 1/3 sigma naught squared. I prefer the top function, so it's related to the J2 theory. So if we can say this f is proportional to J2. So if our plastic strain increments I wrote a partial there, should have had a D. Our plastic strain increments are proportional to partial derivative of f with respect to Sij. You can also say they're proportional to the unit normal that is at that point on the yield surface. So again, with our yield surface, whatever shape that it takes, in this case it's going to be a hypersphere for J2. This unit normal here is going to be in that same direction as our plastic strain increments. Well, it's pretty easy to find what our unit normal is if we have functions Sij Sij that's basically expanding that out. We would have terms like S11 squared plus S22 squared plus S33 squared plus the shear terms S12 squared. Now, here's where I like to use a 9-dimensional stress space. I want to make a distinguishing feature here between the different stress components, S12 and S21. And I'll show you why in just a moment. If we define f that way, if we take the gradient of this, the partial derivative of f with respect to Sij is going to be equal to, well, 2 Sij. If we write it that way, if we want a unit normal that's in the direction of this vector, then we would find the unit normal by the vector kind of mixing my notation a little bit, but that unit normal would be that vector divided by the magnitude of that vector. The magnitude of that vector would be the vector dotted with itself. And the square root of that. Now in this case, for J2, we would have 2 Sij up on top. We would have 2 Smn on the bottom, times 2, and then we take the square root. The 2's will cancel out. So the unit normal can be written in this way. Or, if we want to write it in the vector form, n is equal to s divided by s dot s to the 1/2 power. And later on, we're going to talk about back stresses. We're going to use the symbol xi. If xi is equal to s minus the back stress tensor alpha, then we can also write this in terms of, the xi divided by xi dot xi to the 1/2 power. Now if this is our first excursion out to the yield surface and we are on the yield surface, by definition then s dot s or xi dot xi is going to be equal to 2/3 times sigma naught squared. So this vector n can be written as s or xi divided by 2/3 sigma naught squared to the 1/2 power xi over the square root of 2 over 3 times sigma naught. Again, this is for J2 plasticity. Alright, so now we have a better idea of how to define the unit normal, how to determine it for a particular yield criterion, and specifically for J2. Let's talk more about the relation of the plastic strain increments to the stress increments. We're going to make an assumption that this relationship is linear. There could be other assumptions, but we know if we were to take a look at the elastic strain increments, we could relate that with the fourth order tensor, elasticity tensor, to the stress increments. I wrote that in terms of the stiffness. I should probably write that in terms of a different symbol. Let's just call it D. Or in terms of components, d epsilon ij elastic is equal to d ij kl d sigma kl. So we have this relationship that's linear. It's a fourth order tensor relationship. We can have the same sort of relationship, and that's what this linear relationship amounts to. We can say that d epsilon plastic ij is equal to c ij kl d sigma kl. There could be other assumptions that we make, but this is going to be perfectly fine, and we're going to carry through with this. And basically what we need to do is we need to find this fourth order tensor relationship. Now, just as we have the elasticity tensor for isotropic materials, it only depends on a couple of material properties. We can really reduce this down for isotropic materials that have plastic flow as well. But this is just the general expression. Now this fourth order tensor can be a function of stress, strain, and loading history, but it can't be a function of the stress increment again, because that would make it a nonlinear relationship. Now, because this is a linear relationship, it has an implication based on what goes on at our yield surface. So here's our yield surface. We're at a stress state that is going to have impending plastic flow. Here's the unit normal, and we know that the unit normal can be determined as proportional to F with respect to sigma or S. And we know that the plastic strain increments go off in this direction. And if we're going to have a loading, we haven't talked about the loading criterion yet, but if we have loading, if we have continued plastic flow, we have to have a d sigma vector that points somewhere outside and away from the yield surface. However, we can take that d sigma and we can break it up into two parts. We can have a part of this d sigma that is tangent to the yield surface, and we can break up the other part of it, the remainder of it, that is parallel to the in direction. If we do this, if we notice this tangent part, let me change colors here. If we take in and dot it with d sigma tangent, we get 0. By definition, two vectors who are perpendicular to each other, their dot product will be 0. They have a 0 length projection. If we have loading, however, then our yield surface is going to expand. If we have isotropic hardening, it's going to move. If we have kinematic hardening, oops. The df, the increment of that function, is going to have to be greater than 0. And this loading condition can be expressed as partial derivative of f with respect to sigma ij, and it's in the in direction, dotted with the d sigma ij being greater than 0. Okay, so we're only going to allow loading if we have a stress increment vector that has some portion of it in the direction of n. And if that's the case, the portion that's tangent doesn't contribute to loading. And we can write this down if we want. We can say the partial f with respect to sigma ij dotted with d sigma, let me use ij, parallel plus d sigma ij tangent is greater than 0. But if we distribute this through, the second dot product is equal to 0, so this only amounts to the partial of f with respect to sigma ij d sigma ij parallel. So the only portion of d sigma that causes plastic flow, causes increments to plastic strain, is the portion of d sigma that's in the direction of the unit normal. So our d epsilon ijp then depends on, first of all, the unit normal that we're at. It depends on the portion of the stress increments that is in the direction of the unit normal. And then, to make everything work out, there has to be some scale factor that goes out in front. This would be a scalar d lambda. Okay, so this will be our expression that we're going to use for the normality flow rule. D epsilon ijp is equal to the d lambda n dot d sigma times n. Okay, so scalar quantity, portion that causes loading, and then normal to the yield surface direction. So let's figure out what d lambda is. So we're going to have some assumptions here. We're going to assume that we have an isotropic material. And we have its uniaxial stress strain curve, specifically the stress versus plastic strain that we have defined. And we'll use a Ramberg-Osgood material soon, but that we also have a condition of uniaxial loading to begin with. We're going to expand this to the multi-axial case, but for now we're going to look at uniaxial loading, and we're going to look at the J2 flow theory. Alright, so our stress tensor is going to look like this. We have stress just say in the x direction. All the other stress components are 0 for uniaxial loading. We're going to apply an increment of stress. It's only in the x direction. All the other increments are 0. The corresponding deviatoric stress tensor will be 2/3 sigma x in this position, minus 1/3, minus 1/3 right here. I won't write it again, we've written it down numerous times, the definition of the deviatoric stress tensor. And we're going to use this n dot d sigma n, where we can find our components of n based on deviatoric stresses. Let's write it this way: Sij divided by square root of 2/3 sigma naught, and we are just at the onset of yielding. Kind of mixed my notation here again, but if I want, we can just make this an Nij. Alright, so let's suppose we want to figure out what d epsilon plastic in the x direction is equal to. It's equal to d lambda n dot d sigma. Okay, first of all, n dot d sigma is going to be 2/3 sigma x times d sigma x. And then it's going to be n, and specifically it's going to be n11, 2/3 sigma x divided by square root of 2/3 sigma naught. And actually I need to do this again. I need to square this down on the bottom because I have an n here and n here. That term is actually squared right there. Okay, so I have 2/3. I have a sigma x squared. It's my d lambda. I have square root of 2/3 sigma naught squared. I need another 2/3 on the top, and I need a d sigma x on the top as well. Now if we're just at yield, sigma x is the yield stress, so these two terms will cancel out. The 2/3 will cancel out. And what we have left then is we have d lambda is equal to 3/2 d epsilon x plastic over d sigma x. And we can interpret this then as 3/2, 1 over the plastic tangent modulus h, where h is d sigma x d epsilon x plastic. So if we look at the stress versus plastic strain curve, at any particular point that we're at, the slope of that curve is h. So in general then, let me make a new page. We have d epsilon ij plastic is equal to d lambda n dot d sigma n. And here where d lambda is equal to 3/2 1 over h, where we're using J2 flow theory. Now, if we furthermore use the Ramberg-Osgood material description, and we'll write that down. Epsilon x plastic is equal to sigma x over k to the 1 over n power. That's our power law description. If we rearrange this, sigma x is equal to k epsilon plastic to the n power. If we want h, if we want to find that, it's the derivative of sigma with respect to epsilon plastic. Well, let's see, we've got k times n epsilon x plastic to the n minus 1 we can also write as k in epsilon x plastic is sigma x over k to the 1 over n. So we can write it in this form. K in sigma x over k to the n minus 1 over n power. That's our expression for our plastic tangent modulus. And then the d lambda would be equal to 3/2 times 1 over h. Now, this sigma x value for isotropic hardening can change depending on how far along we are on the curve. Okay, so this would be our von Mises equivalent stress that we would plug in, and we would find the corresponding von Mises equivalent plastic strain. Okay, so as our yield surface expands, our equivalent stress increases, our material softens, the slope decreases. I won't say we have a softening material, but the slope decreases. We're still in a work hardening range, but we can find that plastic tangent modulus. And so now we're building up a way that we can find our plastic strains. Let's summarize on the next page. So first of all, we have to be loading, and we have to have continued plastic straining. We have to be on the yield surface. We have d epsilon plastic is equal to d lambda n dot d sigma times n, where d lambda is equal to 3/2 1 over h, where for a Ramberg-Osgood material, h is equal to k n to sigma von Mises over k, the n minus 1 over n, where we're going to use our yield function to be Sij is equal to 2/3 sigma naught squared where n is the partial of f with respect to Sij. Let's use the notation like that, partial of f with respect to s, which we can find that's proportional to that. But in order to do this, we need to divide it by the magnitude. This top portion for this particular yield criterion is Sij, and on the bottom goes the size of the yield surface it's going to be this term, the square root of that term. We have isotropic hardening, and this is the von Mises stress goes on the bottom. And for any given increment of stress, then we can compute not only the unit normal, but we can also compute n.d sigma, and we can compute this d lambda so we can find our plastic strains. So in general, we could have a multi-axial state of stress. I'll write a few of these in here. Be symmetric. But we take this d sigma, again dotted with our unit normal based on this matrix, multiply it by this matrix, and then we multiply it by dm. It's based on our plastic tangent modulus, and now out pops our plastic strain increments. Okay. So I have already made a video or two where I apply this for isotropic and kinematic hardening to come up with our plastic strain increments using a spreadsheet. Alright, so that kind of summarizes it. Again, we're looking at our Ramberg-Osgood material with our K and N that have been defined as we've done previously. We're looking at, for now, isotropic hardening where the yield surface is expanding, and we're looking at J2 flow theory.